This is a walkthrough for my honors chemistry class on some simple rules on how to balance equations. The first thing you have to understand is how to read an equation. So everything on the left is called a reactant, everything on the right is a product, and then the arrow means yields. So basically the molecules or atoms are getting rearranged and the products then come out on the other side. The numbers in the front are called coefficients, whereas the numbers below are called subscripts. You cannot change the subscripts when you're given a chemical equation. So for example, to balance this equation, you couldn't just add another 2 over here next to the oxygen. You would actually have to add a coefficient and make 2 water molecules, because if you add a 2 here, you're not making water anymore, you would be making a different product. So what you see here are word equations, and this is where we're just given the names of what reacts. However, this is not what we're typically using in a lab. In a lab, we need a chemical equation that shows the symbols. So here are some examples of chemical equations. Here we show iron reacting with oxygen, as it's found in nature, O2, forming iron 3 oxide. This tells me the exact ratio of the elements in the compound. This is not a balanced equation. You'll notice on the right side we have 2 irons, but on the left we only have 1. The law of conservation of matter says that matter can't be created or destroyed. So if I have 2 irons coming out on the left, they had to come from somewhere, and that's where balancing equations is going to come in. Another thing that we might see is we might see what state the reactants or products are in. So for example, this is telling me that solid iron is reacting with oxygen gas and then forming iron 3 oxide solid, which is basically rust. So this is showing the reaction for making rust. Also, if you see aqueous or AQ, that means that we have something that's dissolved in water. Another thing that we might see is a reaction could show a catalyst. So a catalyst, you may have learned about enzymes in biology, and a catalyst is where something causes the reaction to happen, but it does not participate in the reaction, and at the end of the reaction, it is still the same as it was when the reaction started. So in this case, we have peroxide breaking down into water and oxygen. However, manganese dioxide helps this to occur, and the manganese dioxide is not changed by the reaction itself, it's still sitting there at the end. Another one that's not in these notes that you might see is you might actually see a triangle above the arrow, and that means heat. Alright, so let's take a look at balancing an equation. So this is the simple equation for the formation of water. We have hydrogen gas and oxygen gas combining to make water. Now the reason that we have to write the H with a 2 here and the O with a 2 here is because that's how they're found in nature. And last chapter I talked about one way that you can remember that is by using Hofbrinkel. Hofbrinkel tells us all of the diatomic molecules that we find in nature. So whenever we have hydrogen by itself going into a reaction, we need to write it as a diatomic H2. And the same with oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So what we do is we're going to start with how many atoms we have of each element on each side. So you'll notice in this reaction, I put our hydrogen and our oxygen in the center here because these are the 2 elements involved in this reaction. And now we're going to count them up. So the 2 here tells me that there are 2 atoms of hydrogen. Now it's not the same, just for the record. This means this, that we have hydrogen H2. We have basically 1 molecule of hydrogen consisting of 2 atoms. If you wrote it as this, that would mean you have 2 hydrogens by themselves, and you have basically 2 of them. So it doesn't represent the same thing. But when we're counting up, if you had either one of these, this one or this one, you would still have 2 hydrogens on the left. We also have 2 oxygens on the left, so we put a 2 here. On the right, we have 2 hydrogens. However, we only have 1 oxygen. So this equation is not balanced. We need to balance this equation so that we have the same number going out and in. Now, we're not allowed to change, as I mentioned before, you cannot change these subscripts. This is a chemical formula. What we can change are the coefficients, the numbers in front. So we're going to start with the only thing that appears to be unbalanced right now, which is our oxygen. So what I'm going to do is I'm going to put a 2 in front of the water. I can't put the 2 in between the hydrogen and oxygen because this is a water molecule. So what I've now done is I've said I have 2 of these H2Os, like that. Now if I do that, I have fixed my oxygen problem. I now have 2. However, I now also need to account for any other numbers that have changed. And in this case, by putting a 2 in front, I have also changed the number of hydrogens from 2 to 2 times 2, 4. So my hydrogens on the right side are going to change to 4. Now what we need to do is see how that affects our left side. And you'll notice that we only have 2 hydrogens on the left. So now we need to find a way to balance those. If I go up here to my hydrogens and I put a 2 in the front, I would now have 2 times 2, 4 hydrogens. And now I can double check my work. I have 4 in, 4 out, 2 in, 2 out. And so my final equation would be 2 hydrogens plus 1 oxygen make 2 molecules of water. Notice that we didn't change the number of atoms on each side. We still have 4 atoms of hydrogen on the left and 2 atoms of oxygen. We have 4 atoms of hydrogen on the right and 2 atoms of oxygen. All we've really done is rearrange their locations. So let's try another problem from scratch. In this particular case, we have silver nitrate reacting with hydrogen sulfide to make silver sulfide and hydrogen nitrate, or nitric acid. Alright, so the first thing we're going to do is we're going to write down the middle all of the elements that are involved in this reaction. Now, there's 2 ways you can do this, and what I taught my class is that if you have a polyatomic, like in this case nitrate, and it stays the same polyatomic on the right, it doesn't split up, you don't see those elements appear anywhere else, you can actually count that polyatomic as a single thing, like this. So there's 1 nitrate, and then we have hydrogen, and we have sulfur. So now what we're going to do is we're going to count how many of each thing we have on the left and the right. So we have 1 silver on the left. We have 1 nitrate, 2 hydrogens, and 1 sulfur. On the right, we have 2 silvers. We have 1 nitrate, 1 hydrogen, and 1 sulfur. Alright, so now we're ready to start balancing. So we want to look for something that's not the same on both sides, and that's pretty easy. That's going to be our silver. So in order to fix our silver, what we can do is we can put a 2 right here on the left. That will make 2 silvers going in and 2 going out. It will also change the number of nitrates on the left to 2. Now, if we go back over to the right side, you will see that our nitrates are not balanced. Alright, additionally, we will see that our hydrogens aren't balanced either. And you could continue wherever you want to. I'm going to go ahead and go to the right side and fix our nitrate issue. So if I put a 2 here on the right, I now have 2 nitrates. And I notice that this also changed my hydrogens to 2. And if I go back and check, I see that I have 2 of these on each side, 2 silvers, 2 nitrates, 2 hydrogens, and 1 sulfur. And so I am balanced. So our final equation would be 2 plus 1 makes 1 plus 2. And by the way, you don't have to write a 1, it's assumed. So technically it would be this. 2 plus 1 makes 1 plus 2, but we don't write the 1, it's assumed. Now we're going to try a problem that gives you a little more trouble. So here's what's going to happen here. We're going to write our elements like we did before. We have 3 elements here: carbon, hydrogen, and oxygen. This is actually called a combustion reaction because we are typically burning a carbon compound in oxygen, making carbon dioxide and water. Combustion reactions can be tricky to balance in particular, and I'll show you why in a minute. Now, here's the first thing I want you to notice. In a combustion reaction, you actually end up with oxygen in 2 places on the right. So if we go over to the right side, you see that oxygen is here with the CO2, the carbon dioxide, and we also have oxygen with the water. The problem with that is that if you try to balance your oxygens first, you're not going to be sure where to put your coefficient because you could put it here or you could put it here, and so it's tricky. So the first thing that I suggest, kind of a rule of thumb, if you find something like oxygen in 2 places, balance it last. In fact, sometimes you should balance hydrogen and oxygen last. So let's not work with those. Let's go straight to our carbons. So let's go ahead and put our numbers. So we have 4 carbons on the left, 1 on the right. 10 hydrogens on the left, 2 on the right, 2 oxygens on the left, 3 on the right. And be careful because you have to total these up. So you have 2 plus 1. So you have a total of 3 oxygen atoms on the right, even though they're in 2 different places. All right, so I'm going to start with my carbons because I don't want to mess particularly with the oxygens yet. So if I change my carbons, I need to put a 4 on this side. And that gives me 4 carbons, but it now gives me, and be careful here, 4 times 2 is 8 plus this one. And so now I actually have 9 oxygens. All right. I'm also going to now try changing my hydrogens. I'm not going to mess with my oxygens. So I have 10 hydrogens on the left. So to fix the right side, I know that if I put a 5 here, I will now have 10 hydrogens on the right. And this is going to change my oxygens yet again, so that now I have my 4 times 2, which is 8, plus another 5, so I actually have 13 oxygens on the right. Now, this is where the problem comes in. There's no number I can put in front of this oxygen, no whole number, that will give me 13. I would have to put a fraction. So the easiest way to solve these, because you have to give your answer in whole numbers, is this. If you know you need 13, then technically what you really need is 13 over 2. In other words, you really need half of 13. You need 13 over 2 of these O2s. That would give me 13. Now, you can't leave it this way. So the easiest way to now take care of everything is this. We're going to multiply the entire equation by 2. We're going to double everything. By doubling everything, you're basically, when you multiply 2 times this number, it's going to get rid of the fraction. And you'll get a whole number equation. So our final equation would end up being 2 C4H10s, it's methane, plus 13 oxygens make 4 times 2, now 8 carbon dioxides, plus 5 times 2, 10 molecules of water. And we can double check everything. We have 8 carbons now on each side. We have 10 times 2, 20 hydrogens. on each side. And we have 13 times 2, 26 oxygens. And on this side we have 16 plus another 10, and that's 26 oxygens. So that's a tricky problem. But the way to solve these, again, is if you need exactly something over 2, or you need a fraction, put the fraction over 2, multiply the entire thing, and that will cancel out your 2. All right, let's try another one. So we have silver. Again, we have nitrate. I'm going to leave it as nitrate. Calcium and chlorine. And I'm going to go ahead and put in my numbers. One of these, one of these, one of these, 2 of those. 1 calcium, 2 nitrates, 1 silver, 1 chlorine. All right. So the first thing I'm going to do is I'm going to fix my nitrates. So by putting a 2 here, I will now have 2 nitrates, and I will now have 2 silvers. I'm going to jump over to the right now and fix my silvers by putting a 2 here. I now have 2 silvers, and I have 2 chlorines. And you'll notice my equation is now balanced. And you'll see this a lot, that when you work your way back and forth, fixing one thing, like in this case, fixing my silvers, automatically fixed my chlorines. All right, this is trickier because this is now going to be a word equation and you have an extra step. So we want to change this first into a chemical equation. So hydrogen is found as H2. Sulfur is an element, and it's forming hydrogen sulfide, which, if we look up hydrogen on the periodic table, forms a +1. Sulfur forms a -2. All right. And so when you crisscross, yes, this goes back to ionic compounds and crisscrossing, you would get the formula of H2S. Unfortunately, if you don't remember the chapter for crisscrossing, that's going to now come back and cause you a problem because we're building on that material that you already are supposed to know. So our 3 elements are hydrogen, actually 2 elements, sorry, hydrogen and sulfur. We have 2 and 1, we have 2 and 1, and guess what? This is already balanced. Now let's look at an even more complicated one, iron 3 chloride. So that means that iron had a +3, chlorine has a -1. So iron 3 chloride is going to be FeCl3. Combines with calcium hydroxide. Calcium is a +2. Hydroxide was a -1. So this is going to be CaOH2. Forms iron 3 hydroxide. That's iron with a +3. Hydroxide has a -1. So now we have FeOH3 plus calcium chloride. Calcium +2. Chlorine has a -1. So this is going to be CaCl2. All right. So now that we've got our equation written out, we're going to balance. So we have iron, chlorine, calcium, and hydroxide. Again, I'm going to leave this as hydroxide instead of breaking it up because it's hydroxide on both sides. But if by some chance a polyatomic breaks down, you're going to have to separate it. For example, if we add hydrochloric acid to calcium carbonate, we get calcium chloride plus water plus carbon dioxide. Now notice what happened here. Our carbonate on the left is not carbonate anymore on the right. We now have one of the oxygens that's combined with hydrogen to make water, and we have carbon dioxide instead of carbonate. So in a case like this, you can't write that we have hydrogen, chlorine, calcium, and carbonate because it's not carbonate anymore on the right. So in this case, you would do hydrogen, chlorine, calcium, carbon, and oxygen as your elements that are involved in this reaction. But for now, let's take a look at the reaction at hand. So going in, we have 1 iron, 3 chlorines, 1 calcium, 2 hydroxides. On the right, we have 1 iron, 3 hydroxides, 1 calcium, and 2 chlorines. All right, so in this situation, there's no way, if we look at our chlorines, to change 2 chlorines into 3 chlorines. But we're not going to do what we did with the combustion problem. In this case, what we can do is we can find a least common denominator. In other words, if I know that chlorine, that 3 and 2 both go into 6, then what I can do is, if I put 2 of these and 3 of these, I will now have 6 chlorines, and 3 times 2, 6 chlorines. So I'm using a least common denominator in this case. So this now gives me 2 irons, 6 chlorines, and then on the right side we now have 3 calciums and 6 chlorines. So let's go back and try to fix our iron. We have 2 on the left and only 1 on the right, so I'm going to put a 2 here. We now have 2 irons and 2 times 3, 6 hydroxides. So now we need to go back to the right. And I notice that if I put a 3 here, I will now have 3 calciums and 3 times 2, 6 hydroxides. And I'm balanced. Okay, this next section I'm not going to spend a lot of time on, but once you know how to balance equations, another thing that you could be asked to do is to classify a chemical reaction as to what kind of reaction it is. Not every reaction clearly fits one type, but a lot of reactions that you see will, so we want you to recognize 5 general types of reactions. So our first type is called a combination or a synthesis reaction. This is very easy to recognize. On the left, you have 2 things going in, A plus B. On the right, they have combined, or we have synthesized, a single compound. Here's an example. Sodium, chlorine, 2 elements. On the right side, we've made only one thing, sodium chloride. In some cases, like with sodium chloride, we would know that the formula because it is ionic, and we know that sodium would be Na plus and Cl would be Cl minus. In some cases, what we see is that it's not going to only make one possible product. So for example, if we combine sulfur and oxygen, which are 2 nonmetals, we could get sulfur dioxide or sulfur trioxide, 2 possible possibilities. Or if we combine iron and sulfur, since iron's in D block, it could form iron sulfide or iron 2 sulfide or iron 3 sulfide. So in some cases we don't know for sure. In our class we're not going to deal with what possible things can be made, but you should definitely be able to recognize a synthesis reaction. Our second type of reaction is called a decomposition reaction, and it's sort of the exact opposite of a synthesis reaction. We have one thing on the left, and it decomposes or breaks down into 2 or more things on the right. And so you'll see here we have our mercury 2 oxide. It breaks into liquid mercury and oxygen gas. One thing on the left, 2 or more on the right. Our next type of reaction is called a single replacement. And the key to a single replacement reaction is you have one element by itself and it kicks another element out. So notice A was by itself. A comes in and steals X away from B. Sort of like steals B's boyfriend. And now A has a boyfriend and B is all by herself. And here's 2 examples. Potassium steals away hydroxide from hydrogen. Now the potassium is with the hydroxide and hydrogen's by itself. Notice you always end up with one element kicking out another. Here's another one. Zinc comes in, steals nitrate away from copper, and now copper's by itself. Now there is a rule about this, what elements have the ability to replace other ones. And I kind of like to joke about this and call it the Sexyness Scale. In other words, any metal that's above another metal on the scale would have the ability to steal away something from that other element. In other words, for example, if I had sodium chloride and potassium came in, since potassium is above sodium, it would be able to steal away chlorine from sodium. So lithium's sort of like the hottest chick. She could steal anyone from anybody else. And on the other hand, copper would be not very attractive. So if you had copper chloride, for example, and lithium came in, lithium would definitely steal chlorine. But on the other hand, if you had magnesium chloride and iron came in, it would just sit there. The iron metal would just sit there in the cup with the iron chloride and nothing would happen because iron does not have the ability to steal. It doesn't want to be with the chlorine as much as the magnesium. There's also a rule for halogens, meaning fluorine, chlorine, bromine, all of those. And the rule for those is that any element above another, again, would take its place. So if we go to our halogens, they're fluorine, bromine, chlorine, iodine. So fluorine could steal chlorine away, but iodine could not. And also note that if you're trying to decide where the single replacement is going to occur, for example, if you saw NaCl plus Ag, if this reaction is going to happen, you're adding a metal, so it would replace the other metal. This reaction actually would not happen. On the other hand, if you had Cl2 plus NaF, this is a halogen, it would replace the other halogen. So pay attention to what's being added because an anion will always replace another anion, a cation would only replace another cation. Our next type of reaction is called a double replacement. And what you're looking for here, the pattern is you have two compounds and neither of these, notice no element by itself. Both of these have a partner. It's kind of like the show Wife Swap. These two are going to switch places. A would rather be with Y and B would rather be with X. So they switch partners. You don't end up with anything by itself. So you're looking for two compounds and then two compounds just with a switch in the cation. Again, just like with the single replacement reaction, just because you mix two things together doesn't mean they're going to react. And there are some rules that you can look for to decide. One of the rules is that if, when they react and switch places, one of the products would be a solid or a precipitate, that will push the reaction to occur. So for example, sodium chloride and silver nitrate, if you switch the sodium and the silver, you get silver chloride and sodium nitrate. Silver chloride happens to be a solid, and that means this reaction would happen because the fact that it makes a precipitate would drive the reaction. Sometimes the products will actually be unstable, and in this case, for example, carbon dioxide gas will be released. And also, there is a special kind called a neutralization reaction. It is a double replacement. If we rewrite water here as HOH, then technically we do have a double replacement with the hydrogen replacing the sodium. But in a neutralization reaction, an acid, which starts with H, combines with a base, which ends with OH, and you get a salt, which is basically an ionic compound, and water. This is still, though, a double replacement reaction. It's just a special type. These are some solubility rules. This is not a complete list, but solubility means whether they'll form a precipitate or not. So, for example, all compounds that end in nitrate will not be a precipitate. So silver nitrate would be dissolved. zinc nitrate would be dissolved. No matter what you put in front, any compound with nitrate at the end will be dissolved in water. Alkali metals, that's your first column, they're all soluble too. So if you weren't sure and you saw, for example, KCl, and you put that in water, since potassium is an alkali metal, this would always be dissolved in water. And anything that starts with ammonium as well. So all of these, if both products in a double replacement have one of these things, then the reaction won't happen, because all of these products would be soluble. They would all be aqueous. None of them would form a precipitate. On the other hand, here's just a list of a couple of things that do. Chromates, sulfites, carbonates, phosphates, and hydroxides. All of those are examples of things that would, for the most part, form a precipitate. So if you were mixing, for example, let's say sodium sulfate with, let's just say, iron nitrate, would this react? Well, the answer is yes. Sodium sulfate is going to be dissolved, and iron nitrate is going to be dissolved because it has a nitrate. When these switch places, you would now have sodium nitrate, which would be dissolved, but iron sulfate would be a solid. So that would be an example. And in AP chemistry, you actually would have to memorize all the solubility rules. Just a heads up. So here's a quick example. Sodium chloride is added to a solution of potassium hydroxide. And the question is, would they react? Well, if sodium and potassium switch places, we'd get sodium hydroxide and potassium chloride. Sodium and potassium are both in the first column of the periodic table. That means that they would not, neither of those would be a precipitate, so they would not react. On the other hand, sodium carbonate is combined with iron nitrate. Well, right now, these would be dissolved because iron nitrate has nitrate in it, and sodium carbonate has sodium in it. But when we combine them, we would get iron carbonate, and carbonates are insoluble. So this reaction would happen, and in fact, when you mix them, you would be mixing two dissolved things, and you would actually get a powder, a precipitate, forming in the bottom. The last kind of reaction is a special reaction called a combustion reaction. What happens in a combustion reaction is something is burned. In fact, a lot of times you would see a triangle here. And the unique thing about a combustion reaction is that it always follows the same pattern. We have a carbon compound, in this case methane, reacting with oxygen. It makes carbon dioxide and water. Other examples of combustion reactions would be, for example, propane, which is what you have in your barbecue grill, or butane, which is what's in lighters or lighter fluid. And so these are examples of carbon compounds reacting with oxygen, and if they fully burn, that's called complete combustion, everything gets turned into carbon dioxide and water. Sometimes, if there's not enough oxygen present, we have what's called incomplete combustion. This is like, for example, when your car makes exhaust and you have carbon monoxide gas, or certain generators, things like that you're supposed to burn outside. But for the purposes of our class, just know this kind, the complete combustion, that it's always going to be a carbon compound reacting with oxygen. Typically, we're talking about burning, and our products are going to be carbon dioxide and water.